Okay, welcome back to this second part of implementing the LDSO Twitch version. Welcome back. We will continue with the main function now and we'll implement, so to say, the main part of the algorithm. Many things will be included here which we will not have in the beginning, so we need to create them along the way, but we will create placeholders, I would say, to later fill up those missing parts. What we want to achieve today is to be able to parse the arguments that are passed to our program and use those arguments to load up the dataset. But I think the dataset will be not loaded in this part, but in the next part. Let's try to conceptually at least discuss the main function and implement it. So that's the main goal for this video. Okay, so we have this main function here, which basically implements our hello world example, and we can run this this program. I will show that again. So I'm here in this folder structure, and I can simply change into the bin directory where the executable is compiled, and then I can run this executable and hello world will be printed onto the console. We will now try to make it a little bit more interesting. So let's change directory to the main directory and maybe even to the parent directory, because here I have one shell script to run the original LDSO code base, and I will now copy this file and will create a shell script to run our new version, the LDSO Twitch version. So let's copy that and rename it to run LDSO Twitch sequence. And let's open it up, maybe with the studio code. Okay, now we want to switch not in the LDSO directory, but into the LDSO Twitch directory, I believe. LDSO Twitch, it's like that. And here, of course, it should be run LDSO Twitch. Run LDSO Twitch TUM Mono. Okay, we will use the TUM Mono Dataset, which is a photometrically calibrated dataset. And therefore is using images, not only images, which you can see here, but also a vignette and a geometric camera calibration and a photometric camera calibration. We can also define a preset, and those arguments will be passed on to this executable file, and they will just set different settings, because there is a lot of settings, and initialize our main program to be able to run on those, on that data, basically. Okay, so this should be fine. The dataset we will be using will still be the TUM Mono dataset, the sequence 45 to be specific here. And maybe I can show you where you can get that. So TUM Mono. Let's just Google for that. I just Googled for TUM Mono, and then in the vision.informatics TUM DE, you will find this monocular visual odometry dataset, which you can download here. So you can download the individual sequences here as the zip file, and you can even preview the video here. So this is one of such videos, for example. Okay, I have downloaded that. The sequence 45 it was, I think. Sequence 45, this is this one here. And of course, we can later test different data sets, and we should also test them. Let's just preview that. It looks like this. You should note from the first part, it was used to not only show the loop closure, but also show the general operation of the LDSO. Okay, let's go back. So this should be fine. And if I save that and I run that, I have this LDSO Twitch sequence. Run LDSO Twitch sequence. Then once again I get hello world, but this time the arguments preset, files, vignette, and so on are passed to this main executable. We can test that by trying out if we have received the arguments, for example, by printing the arg count, the argument count, and also maybe with an end line printing the argv. Let's say if that works. So end line. Okay. No complaints, so let's try it out. Of course, first we need to compile the project. So I will make a new tab. It's a little bit cumbersome to compile that using the terminal. I think later we will also create a launch configuration for Visual Studio Code to be able to run it faster and compile it faster with one click. But for now, I will leave it like that. Okay, it was compiled. Now we can run that again, and we will see that we now have 7 arguments. Let's quickly count that. So 1, 2, 3, 4, 5, 6, and the first one is the name of the executable. So this should be 7, that's fine. And of course, we do not get the string for the individual, for the array, but we get the memory address where it is available or stored at the moment. And this is not useful for us, but we know that this is correct for now. Okay, so we can delete that. It's obviously working. We didn't check what is passed inside, so what are the argument values here, but I think we can work with that now. Alrighty. Now, what do we want to do here in the main function? First of all, we will write a to-do because we need some includes. We'll leave that for now until we really need that. I will add those to-do commands from time to time to be able to later find the places or the important lines in the code where we need to add something later, because it's a little bit complicated and we should only go step by step and not try to to implement everything. I believe it's in my view the correct way to approach this, and just concentrate on individual parts and not trying to just code up everything and then try to run the code. But I would like to run the code each time we have accomplished a specific part of the implementation, such as parsing the arguments today, I would say, and later read in the dataset and then run the dataset, and so on and so forth. Okay, so we need to add some includes here. So this will be, for example, libraries. But we will also add some includes for what is the main part of this algorithm of the full system, for example. Let's put it in quotation marks, because this is something that will be or will have the same value, I would say, as the main function. It will be basically the main function in my view. Okay, then next we will have to add the parsing functions. So we take the arguments that are passed onto this program, and we need to then parse the arguments. Okay. For now, let's continue with the main function. Let's quickly think about what will be done in the main function as a first step. Of course, we can print, for example, the hello world, but usually when we have the main function, we want to start doing some useful stuff. And for this, we can define a variable, which is called flags, not flags, but flags. Color log to standard error equals true, so that we can have colors in our terminal. And then we start by parsing the arguments. So we take our argument value array here, and we loop through that using the argument count. So we write a for loop, and we have this integer here for the argument count. We start by I equals 1. Why? Because the first argument is the name of a program, which is not very useful for us because we will not do anything with the name of the program, but with the other arguments. So we repeat that until we have the iterator variable, the I, equal to argc, and we will stop. And then we increment. So this should be everything. And here we will use a function that we will define, which is called parseArgument. Which argument do we want to parse? We want to take it from the argv array at the position I. Simple as that. We can, of course, also just print the current argument. Let's write it like this. Parsing argument equals, and then we can add the I variable. Something like that, I would say. Okay, now we have two errors because this is not known, this variable name. So we'll have to introduce it. And the question is, where is it located? And I'm not quite sure, but I think it is from the Google logging library, the glog library. So we need to include that by writing glog and then the logging.h header file. Okay, now this first error is gone. And of course we also need the parseArgument method, or in this file, in this case it's a function. So we create a void function called parseArgument. Maybe let's try to refactor that. Go to definition, it's not available. Okay, let's type it the traditional way because I don't know my way around in this Visual Studio Code tool. So let's just write void parseArgument, and then we have one star less because we now have a string, so a char array, an array of characters, and we call it arg. And now we fill the body with the logic. So we can now also move this this terminal output to this method body or this function body. Or we cannot do that, sorry, because we do not have the arguments or the variables here, of course. Okay, let's quickly test that. Let's compile and run that. Okay, so now we can see that the arguments passed here are, the 0th is not being displayed here, but it's exactly what we have passed here. But we have a problem because we need to separate the argument name by the argument value using this equal sign here. And this is what will be done in this parseArgument function. So first we define an option. And what is the option? I'm not sure. It's used in the scanf file function. And I'm not sure what this means at the moment, but we will clearly find out. Then we get a float option, f option. So we have an int option and a float option. So this is basically what the scanf function will tell us, what is included in this argument here. Let's be more specific in a second. We create a buffer for characters with 1000 with a size of 1000 characters. Next, we will check if the scanf function, which consists of the actual string that we are passing, we are just passing the argument character array here, and a specific format you are looking for. And then there's something else which will allow us to pass the option that we just generated here. Okay, so what do we want to pass? We want to pass the argument Next, we want to check if this argument contains a specific structure. In this case, we will look for one argument which is called sample output. And here we are expecting a %d, which stands for an integer. So we need to also pass our integer that we defined here, the option, which will get the value that is written after the sample output. So in this case, we just pass a reference to the option variable, and that's it. Now this scanf function will return an integer, which will tell us if this argument was found or not. So we need to check that as well. So we just test that if the scanf function will return a 1. Oh, we have a chat. Hi, I want to offer promotion of your channel, viewers, followers. Aha. Thank you very much, but it's a little bit too early for that. Okay, so next, what do we want to do with the option? We want to check this, of course. So if the option is equal to 1, so let's say we have passed the argument sample output equals 1, then we want to do something. What do we want to do? We want to set a specific setting, which is called use sample output equals true. And next, there's also a little information for us that we are actually using sample output wrapper. In the original LDSO code base, it is defined with the printf statement, but I would stick to the C++ way and use the cout statement here. And we'll just say that we are using sample output wrapper now. And we also use the end line so that this will define a new line in the terminal. Okay, now the use sample output is not known. We need to define that. And we can just define it here. Also need to have a to-do. What this means is that the main executable, the main function, will have to store some initial data. For example, initial data which points to a standard data set. For example, if we do not pass a data set using the arguments, the LDSO should still use some kind of predefined data set. Usually this is not necessary because we can simply enforce to have a data set passed as an argument, but yeah, for completeness, the LDSO defines this standard data set. And some variables as well. For example, this use sample output. And this is false in the beginning, and it is of data type bool. So we just make a switch and say, do we want to use it or not? The sample output, as far as I know, is used to output specific information from the LDSO in a specific format. For example, as a file. But you can also use your own output wrapper to output the, for example, the generated point cloud, so the map, as, for example, a website, or upload it onto the internet, and various other ways. So this is what it is used for. This sample output is predefined. We'll create it over the course of creating the LDSO Twitch version, and therefore we just take it as given at the moment. Okay, there are other variables here. I will add them now, just for the sake of completeness, and this way we can delete this to do them. So in the beginning there are standard strings defined, for example for the vignette. And now the interesting part is that in the original LDSO code, this path is pointing to media and then Gao Xiang. We will not do that because we have a different file path, and this of course depends on where you have downloaded your data. But in this case we have it here given. So now let's use that. That's the vignette we need now. Okay, this will not work because this executable is in a folder which is called bin, and the bin folder is in LDSO Twitch. And then in the parent directory we have the vslam datasets. So this will probably not work, but let's leave it like that for now, because we will not use the standard settings anyway. We just need to define them, because later we will set them in the main function. Okay, next we have another string called gamma calib. And this is our gamma calibration, so basically our photometric calibration. And this is given here. This is a text file. And that's it. Then we have another string called source, which tells us where all the files are located. And this is simply the folder with this sequence 45 in my case. In the original code, they have used the sequence 31, for example. Okay, next we have the string called calib. And here we are using the camera.txt file. So maybe to distinguish this better, let's sort this a different way. And let's maybe describe that. So this is the photometric calibration. Oops, I'm missing a semicolon here. That's the geometric calibration. Yeah, this is the source path. And next we need, so this is the data set. This is the minimum information we need to have about the data set. And next we want to define another string called the output file. And this file will be generated during the operation of the LDSO to have our results stored somewhere. So the results are usually the trajectory. So how did the camera move? That's the results.text, and that's fine. And as a last string here, we have the path to the vocabulary, the voc path. Which is stored in the vocab directory. And then we have this dbo3 file. Let's quickly check if we have that. So in the LDSO Twitch folder, we are looking for a vocab directory and it's not here. So we probably need to copy that from the original code base of the LDSO. You can see that here the obvoc.dbo3 file is located, and this is what we need. So we just copy that and put it here. You can, of course, create those vocabulary files yourself for a specific data set or for specific features, in this case, the org features. But we will not look into that in this stream here. Okay. This should be everything. And next we need to introduce a few more variables here. For example, we have a double, which is called rescale. And this is set to 1. Then we have a Boolean reverse play is false. Then we have a Boolean disable ROS is false. We have an integer. Sorry about that noise. We have an integer start index 0, and we have an end index idx is 100,000. So this is the index of the starting image, or let's say the first image, and this is the index of the last image. We can use those indices, for example, for iterating through the dataset, and of course we need to get this information from somewhere, from a specific dataset reader, which we need to implement. Then we have a Boolean about the prefetching the dataset. Then we have a float for the playback speed, which is 0. And the explanation is that 0 is for play as fast as possible. Otherwise, it is a factor on the timestamps. Not sure at the moment what exactly this means. We will find out during the stream. Then we have a Boolean for the preloading, or preload it's called, which is false in the beginning. And then lastly, we have our use sample output that we already have defined. Okay, before I forget, we also want to use the namespaces, because in the include files here, for example, the IO stream, you've noticed that I'm using the standard namespace here, and it would be a bit nicer to not be forced to write that every time. So I can just define using namespace and then std, for example. And I can also use the namespace LDSO, which we will define ourselves. Currently there's an error because we didn't define this namespace. And that's a bit of a problem for now. So let's mark it as a to-do for later. And then weirdly, this using namespace is appearing again in this line of code here, or at this line, which I will not add to my implementation because it seems like a duplicate to me and I do not understand why it should be like that. So let's leave it out for now. Okay. Now let's test it. Let's see if this still works. So let us compile that again. It's working. And this is still working. Okay. So I have not forgotten to add a semicolon, which is nice. Okay, let's continue with the parseArgument function. And let's copy this area for the if statement and add another check for not sample output this time, but for the option quiet, which is also an integer. And that's why we will also check if this option is equal to 1. And then we will set a setting debug out run quiet equals true. And then we will print quiet mode. I'll shut up. Now we have the problem that we do not have this setting here, and we need to introduce it, which brings us to some implementation specific decision to have a file with all the settings. I will quickly check that in the meantime. I think I have found that. But now I need to check where it is included. It's not included directly, but indirectly via another file. And this is the dataset reader. And there's the settings.h. Oh man, this is getting complicated. How to do that without making it completely complicated for viewers. I will define that as a to-do for now until I have a better idea, so that we can continue. Okay, next we want to check for another argument, which is called the preset. And this is something we are passing on here. Preset equals 0. So this is something we can use now. This is of course also an integer, which is available in this option later. But we do not check the option here, but we will make a separate function that is selecting the correct preset for us. And this is called the settingsDefault here. And we pass the option. And then we return. Now, quick fix here. No. I thought I can simply add this function. Not sure. Okay, let's do it manually. So we scroll up and we add a comment, of course. Select proper preset. What is a preset? A preset is consisting of specific setting of detectable feature points in the images and various other things like real-time performance. Do we have photometric calibration in our data set? Do we not have that? Do we only have geometric calibration? This is something we need to decide in this function here. So, for example, a number of feature points, calibration mode, etc. for now. Okay, we have this function settingsDefault, and we now need to define that. This is a void function, and this option will then be passed as a preset. Okay, here in the beginning we will add a cout and an end line, which we write as this interesting preset settings heading. And then we need to decide. So we have this preset given as an argument to this function. And if this is 0, or if the preset is 1, then we want to do something. Because we want to print what kind of preset do we have here. Let me quickly adjust the music here. Okay. So we want to print something to the console. And this is the default setting, or default settings. And now we will add various information here. For example, we will have this S. No, wait a second. It's. Oh, I see. Okay. It's a conditional statement for preset equals 0. Something's not working here. Okay, if preset equals 0, if this is true, then we print no, and else we will print 1 times. Okay, and after that, we print real-time enforcing. So either this is printing no real-time enforcing or 1 times real-time enforcing. Something is missing here. Okay, next we will print the number of active points, which is 2000 in this case. Then we have 5 to 7 active frames. Then we have 1 to 6 LM iteration. I think it's iterations, each KF. Which means, as far as I understand it, that's Levenberg-Marquardt iterations, each keyframe. So the Levenberg-Marquardt is, I would say, the main algorithm behind optimizing for an error term, which is called the photometric error in this case. And this should be done 1 to 6 times. It is a setting, obviously, that determines the real-time performance of our algorithm, but also the accuracy, because we want to have this as accurate as possible. The error minimization should be as best as possible, but this is a little bit of a hyper parameter, let's say, which we need to define for our specific case, for our specific data set. It's not easy to decide that in a general case, in my view. Okay, so as a last point, we have the original image resolution. And this is it. When I've saved that, it should be okay. So after we have printed that information, we need to set that as well, of course. So we need to set the playback speed. It is equal to preset equals 0. if this is true, then we want to set it as 0, else we want to set it as 1. Then we need to set the preload to the preset if this is 1. So preload is true or false depending on whether preset is set to 1. Then we have a setting which is called the desired immature density, and this is 1500. Then we have another setting which is the desired point density, which is set to 2000. We have another setting which is the min frames, which is set to 5, and we have a setting for the max frames which is set to 7. So this is the active frames here, and next we need to set the Levenberg-Marquardt iterations. So let's set it here, setting max opt iterations equals 6. And another setting, minimum optimization iterations equals 1. So 1 to 6, that's what we need here. And because I'm a little bit picky about the ordering, I will set it like the frames here. Okay, and lastly we have a setting for the log stuff, which is false. Okay, unfortunately we do not have the settings at the moment, so once again I will mark this as a to-do. Okay, so this was the case for preset being 0 or preset being 1. Next we have to distinguish between whether the preset is equal to 2 or preset is equal to 3. And then we want to print some other information, which is not the default setting but the fast setting. Okay, now we need to change this preset equals 2 to no or 5 times. It's still real-time enforcing after no or 5 times. And next we want to have only 800 active points and 4 to 6 active frames and 1 to 4 Levenberg-Marquardt iterations for each keyframe, and not the original image resolution, but it's a hard-coded one, 4 to 4 times 320 image resolution. And that should be it for the terminal output. Next we want to set the variables, so the playback speed is equal to preset equals 2. And if this is true, then we set the playback speed to 0. Otherwise we set it to 5. Because this is given here in this conditional statement. Preload will be set to preset equals 3, which will return a true or a false. And next we want to set those settings here from the top, and I will just copy them and paste them here. because they are the same as above, but not 1500 image density points, but 600. And the point density will be set to 800. The min frames will be set to 4, max frames to 6. Max optimization iterations. Oh, it's the minimum. Sorry, the minimum is 1 still, and the max is now 4. And we have 2 other settings here as well, which are called benchmark setting width is 4 to 4, and this other benchmark setting height is 320, and log stuff is still false. Okay, and then we have a line printed in the terminal, which just consists of a few equal signs. I will not count how many, because this is not really important at the moment. Okay, I will remove the standard namespace selector here. Because we are using the namespace now, and therefore I can remove it. Okay, it starts to get quite complicated, but I think it's still manageable. It's just a few if statements. And of course the confusing part is what kind of settings do we have and what do they actually mean? So what is this min frames and max frames? How does this relate to the usual operation of the LDSO? We'll find that out during writing the code. But for now, we take it as given. Okay, so after we have set the default settings, I think we can just test it if it at least prints something onto the terminal. So let's build the project. There's it's an unused option. That's okay, because we are not working with float options and with string options at the moment. So let's run it again, and we see that the preset is set to 0, and therefore the preset settings will tell us that we are using default settings. So we have no real-time enforcing, and we have 2000 active points, and so on and so forth. So this is obviously working. Let's check it if it makes sense. Preset equals 0 will print the default settings. Okay. We have to pay attention that we do not forget to implement or to introduce those settings. But I think eventually, when we are using those settings in the optimization, for example, then we will see that. Okay, settings default, that's it. And now we need some other conditional statements. So bear with me while I introduce all of them. Let's copy that quite statement here. And we now need to check for the rec. Oops, rec argument. And this can be 0. Oh, I forgot something. I just noticed. After this inner if statement, I need a return. because once we have checked for the argument, we want to return from that function and not continue with checking for the other arguments. So let's add the return here. Here it's already included, and we need it here. Sorry about that. Okay, so this can be 0. And if this is set, then we want to disable reconfigure. We do not have that, unfortunately. This is probably something, yeah, it's a variable included in the settings file. We still need to create that. So unfortunately, I need to add another to-do here. Okay, what is written on the terminal? It's disable reconfigure. Reconfigure is something specific to ROS, the robot operating system, and therefore we will not use it in the stream, I think. However, it would be interesting to link the LDSO Twitch version to the ROS environment so that we can use a real-time camera connected to our computer. Yeah, let's see what the future brings. Let's just finish this version at first, and then we can think about other extensions, of course. Okay, so this will be printed, so that's fine. And now let's also check for the no ROS argument. And here the option can be 1. And the reconfigure will be disabled as well. But also ROS will be disabled. So there's a variable called disable ROS, which is set to true. Now this terminal output reads disable ROS and reconfigure. Return. And that's it. And now we need to add another conditional statement to check for no log. No log is another integer, and this can be 1. And if it's 1, then we need to set a setting log stuff equals false. I think this setting was defined here, wasn't it? Oh no, it wasn't. Okay, so it needs to be a to-do for now. And we need to print something useful here, which is called disable logging. And then we return, and we check for another option. So it's a little bit boring here, sorry about that. But of course we need to configure our vSLAM system, and there are a lot of options which need to be set usually to have most flexibility. And another such important setting is, for example, if we want to play the dataset in reverse. Reverse play equals an integer, which can be 1. And if this is set, then we set this reverse play to true. And we print to the terminal that we are reversing the dataset. There are different reasons for reversing the dataset. Mostly it's about the visibility of the feature points in the images. Because if we reverse the dataset, we will see them longer. They can be tracked longer, and this will impact the performance of the Visual SLAM systems. Okay. Reverse, return, and that's it. Now we need to add another argument, which is the no GUI, no graphical user interface, option equals 1. And if this is set, then we want to disable all display and set it to true, which unfortunately again is not defined, so let's make it a to-do. Reverse play, no GUI. Then we have another no MT, which stands for multi-threading. So we need to set, I believe this multi-threading is not set anywhere yet, multi-threading equals false. And we print no multi-threading here. Next, we want to set if we want to prefetch the dataset, which is also an integer, which can be 1. And if this is set, then we want to set the prefetch option to true. And we want to print we are prefetching, prefetch, and that's it. Next we have the start. We can define specific start, which is interesting for a dataset. And this can also be an integer. And we do not check that here, but we quickly say start idx equals option. And we still need a cout, which tells us where we start at, and then we print the start index like that. And then we return once again, and we do the same with the end index. So here we ask for the end argument, and here we set the end index as the option, and we tell the console to print end at, and then end index. And then we return. This is it. Okay, now it gets a little bit more complicated, but not a lot, because now we are asking for the loop closing. Loop closing. What is loop close? What is loop closure? So the LDSO stands for direct sparse odometry with loop closure, and loop closure is helping us to close the loop. So to optimize the whole trajectory when we are running in a circle with the camera, for example, then we want to have a closed circle and not an open circle. Okay, so we are extracting that here, and if the option is equal to 1, then we have a to-do for now. It's a setting enable loop closing, which is equal to true. And else we have another to do, setting enable loop closing equals false. And then we print if the loop closing was set, loop closing, and then we print the setting enable loop closing, which we check to either be enabled or disabled. And we need to put that in parentheses so that it is evaluated. But we unfortunately do not have this variable, so in this case we put the cout in a to-do as well. Then we return and continue with another condition. Which is called files. And this is where it gets interesting because now we want to pass where do we have our images, for example. And this will not be an integer, but this will be a string. So we need to not use this integer here, but our buffer with those 1000 characters size, the size of 1000 characters, and we set the source equal to buff, and then we tell the user that we are loading data from, and then we print the source. It's actually printing the C string here. It should not make a difference in my view, but let's keep it like that for now. Okay. Next we have the vocabulary. Vocab. It's also a string where we set the vocab path. Vocab path. The voc path, sorry. Voc path equals buffer. And then we say we are loading vocabulary from the voc path C string. And that's it. Next, after the vocabulary, we have the calibration. Calib is equal to the string. We put it in the buffer. We set the calib variable. And we are telling the user that we are loading the calibration from the calib C string. So those are the important bits here. Let's now continue after the calibration with the vignette. We are putting the vignette here, and we are loading the vignette from the vignette C string. And then we have a gamma, so our photometric calibration, which will be set as gamma calib. Then we are loading the gamma calib from the gamma calib C string. Okay. It's not over yet. Unfortunately, we have other arguments, such as the rescale. And this will be a float, so a %f. And therefore we need to use the reference to the float option. And we will use it here, f option. And this will be set, this will set the playback speed. And we print that playback speed is set to playback speed. Next, we want to have the output as an argument as well, which is a string. Therefore, we need to use the buffer here. Buff. And we set the output file to buff. And we say output set to, and then we have the output file. And then we return. Okay, the difference here is that now we are logging an info for the user. And we use the Google logging library here, which can log us a severity, which can be info, for example, or probably also error or something like that. And this will log that probably in capital letters and probably with another color as well. Okay, output set to output file. There's no exclamation mark in the original code, but I will leave it here for consistency's sake. Okay, next we have another argument. Who would have guessed? It's safe, and this is an integer again. So we put the option here. Then we have the option here, or it's different now. We need to check if the option is equal to 1. And if that's the case, then we set the debug save images to true, which is not defined yet to do. And then something weird is happening in the original code, because there are some if statements. I will just copy them for now, which ask for 42 equals system, and we make the system call to remove and force recursively images out. And here we want to print something, which is weirdly enough saying system call returned 42. What are the odds? This is only here to shut up the compiler. And then we make an end line. And this is repeated 3 times. Because now the make directory is called with images out. Then remove rf images out is called again. And then the directory is made again. mkdir images out. Yeah, I don't know how to comment that. Not really sure what this is doing. It's just weird. I do not believe that this is throwing a compiler error. Why should that throw in compiler error? It could be a runtime error in my view. But why this is necessary, I don't know. And I'm tempted to remove that. But I do not want to destroy the implementation by removing this stuff. But maybe can make a to-do here. Do we really need that? Interesting conditional statements. Let's call these. Okay. But still, there is a cout statement that we want to save the images. And then we have an end line, and this should be fine now. Of course, we need to delete that part, and we want to return. Okay. Let's again check for the music here. Okay, almost done. We need to copy that part. Well, we don't need to, but I want to. And ask for the mode. So there's a mode we can set. And there are 3 different types of modes we can set. Either the mode 0, which will then let me quickly think how I do that here. Okay, so if the mode is set to 0, then we will just print to the terminal or to the console that we are using the photometric mode with calibration. And that's it. But there's also another option. namely option equals 1. And if this is set, then we have the photometric mode without calibration. Which requires us to set some settings, which there are 3 of them, which is the setting photometric calibration equals 0. And we also have 2 other settings, which is setting affine opt mode equals mode A equals 0, and the affine opt mode B equals 0. And there is an explanation. I will just type that here. -1 fix and greater or equal to 0 optimize with prior if greater 0. Okay, this is maybe a little bit confusing here, but it says that if we have the setting here set to a negative number, -1, we want to fix those parameters. So it obviously has something to do with the optimization, and there are affine parameters, parameters A and B, which can either be fixed during the optimization or they can be optimized. And specifically, if we set it to a number greater than 0, we also want to optimize it with a prior. We will see what that is. It has something to do with the photometric calibration, because if we have a data set that is not photometrically calibrated and the image brightness is changing over time, then this will deteriorate the performance of the photometric or direct visual SLAM, and therefore we need to compensate that during the optimization, and this is a setting how we can do that. Okay, and last option we have here is the option equals 2, and this is saying photometric mode with perfect images. And this is setting the photometric calibration to 0 as well, but this time, because we have perfect images, for example from a simulation, we will also take a look into that. I think during the development of the LDSO Twitch, we will create synthetic images to test the algorithm or to maybe look into specific effects. So we fix those parameters by putting here a -1. And we also need another setting. Setting min grad hist add. Whatever this is, minimum gradient histogram addition probably, but I'm not sure, to be honest. Return. And we can remove the rest here. Okay. In case we have returned or moved or stepped to this line number 314, we want to print something on the console, namely that we have failed and could not parse argument. Which one? The arg. And let's add some exclamation marks, because that's always nice to have, yeah, stressed that something went wrong. Yeah, and that's the end of this function, which is called parseArgument of a string, basically. So we have quite a lot of to-dos here still left to add, but those are only variables we need to introduce in a separate file, which is called the settings cc file, or settings.cc. And I don't know when we will introduce that. Currently it's not really necessary for the operation of our program, but at some point we will have to add that. Okay, but the good thing is that we can now concentrate on our main function again. And here is the place where things get interesting. So let's continue here. Next, we want to see and check for a setting conflicts. We want to check if the setting for enable loop closing, and we have the setting for point selection unequal to 1. In this case, we want to log something, namely an error, to the console, which tells us that the loop closing is enabled, but point selection strategy is not. Is not set to LDSO. Therefore, we need to use the setting point selection to 1, please. And an end line. Now the problem is that we do not have these settings defined yet, so this is a to-do. But by the way, after we have printed the error, we also want to exit the program. So maybe to explain it a little bit, so the loop closing is using feature points. In this case, I think these are orb features. And using those orb features, we can detect loop closure candidates. And of course, to do that, we need to have a specific point selection method, which is using those points. And if this is not set correctly, then of course we have a conflict and we want to exit the program. Okay, next, if the setting show loop closing is set, so if this is true, let's keep it like that, then we want to log a warning this time, which is telling us that show loop closing results is activated. The program will be paused when any loop is found. And we add an end line. Okay. Once again, unfortunately, this is not yet defined, so we mark it as a to-do here. Okay, and I think that to-dos will now be, there will be a lot of to-dos here, but I will still try to add the main logic here, even though it's just a comment, so that we have the main functionality in place, and then in the next part we will add in the implementations of those lines. Oh, my spacing is off. Weird. Okay. Next we make a shared pointer, and this is where things get, well, there's actually some functionality for the first time, which is a shared pointer to an image folder reader, which we need to create still, which is called the reader. And we pass a new image folder reader, which is the image folder reader, and then the dataset TUM Mono. We also add the source, calib, gamma, calib, and various other parameters, such as the vignette. So what this will do, it will create a reader which takes in the path to the images, to the vignette, and the calibration files. Maybe I will show you that, how that looks. So if we take a look at the VSLAM datasets, the sequence 45, then you can see this is how the vignette is looking. So it's a bright image with a darkening to the edges. This is the vignette image. Then we have the photometric calibration, which consists of a simple line with many values that range from 0, which is here, to 250 approximately, with various, oh no, it's 255, sorry. So 0 to 255. And in between there are values that, that just are different sample points, how we should take the images and how we should adjust the gamma curve. So basically, let's say the brightness. It's not really the brightness, but let's keep it like that for now. And then we have the camera.txt file, which which consists of the distortion parameters here and the image resolution and a specific setting if we want to crop the images, so if we want to rescale the images, for example. I think that's everything, and the images are zipped here. I will not unzip them for now, but those are the images that you saw in the beginning when I showed you the video from the website of the TUM Mono Dataset. And this is where, of course, the most interesting part is included, because those are the images we are using for the localization and mapping. Okay, let's comment that out with a to-do and continue. I'm curious how many lines will be left which are not commented as a to-do. Okay, we have the reader that we defined previously, and now we want to set the global calibration. Then we need to check for the setting photometric calibration. Is it greater than 0? So we check for the setting, and we also want to have the reader telling us the photometric gamma. So get photometric gamma, and if this is equal to 0. If this is the case, then we want to log an error to the console, which says error. Don't have photometric calibration. Need to use need to use command line options mode equals 1 or mode equals 2. And of course we want to exit that. Exit with the code 1, because this way we cannot operate. So the LDSO has quite restrictive requirements on the dataset. Okay, before we do the next part, let's add the to-do here. So the reader is not finished now, but also we have to do the settings as well. But we can start with this part. So we define an L start, which is equal to the start index, and we define L end, which is equal to the end index, and we define a L inc equals 1, and this is for stepping through the individual images in the main loop. But we also want to check if we want to reverse the playing of the images. And in this case, we log an info, which tells us reverse with 4 exclamation marks. And we set the L start is equal to end index -1. So we just switch the start with the end index and check if the L start is indeed greater or equal to the reader, and there are the get num images. So we see that the reader will also provide the total number of images if we want to. And in this case, if this is true, then we set the L start to the reader and extract the number of images. Get num images -1, because we start with the index 0. And after the if statement, we set the L end is equal to start index, and L inc is equal to -1. Okay. This should be fine. Unfortunately, we do not have the reader, so we need to add another to-do here. And this should work. Okay, next I will add a comment maybe. Note the orb vocabulary used for loop closure. So we need a shared pointer of type orb vocabulary voc of new orb vocabulary. And then we use this shared pointer using the dereference operator, and we load the vocabulary that was passed via the arguments, or hard-coded into this CC file here. Okay, unfortunately we do not have either the shared pointer nor the orb vocabulary yet. So once again we add a to-do here. Okay, next we will add another shared pointer for the so-called full system. The full system is really full, as you will see, because it's the main part of this implementation of the LDSO. We pass a new full system, and the full system just takes the vocabulary from before, and this is it. Then we call full system, and we want to set the gamma function using the reader, and from this we get the photometric gamma, of course. And then we call full system again, and we set the option linearize operation to playback speed equals 0. Yeah, so the linearize operation is I think, a somewhat weird name for just setting the playback speed. But there's probably more behind that, which we will explore in the next parts. Okay, so once again we need to comment that out. And now we want to introduce something that we can see on the screen, which is again a shared pointer to, this time, the pangolin DSO viewer, which we call the viewer, and this is equal to null pointer. And then we check if we have disabled the display. If not, disable all display. Then we want to initialize the viewer by saying the viewer is equal to the shared pointer which holds the pangolin DSO viewer with a new instance of the pangolin DSO viewer with some parameters, namely a parameter WG 0 and an HG 0 and a parameter false. So what does this tell us? We want to create a pangolin window basically with a specific width and height, and I don't know what this false parameter is. We'll see then. Next we have the full system again, and for this full system we want to set the viewer to our currently created viewer. Okay, if the display is disabled, then we want to log an info that the visualization is disabled. And then we end the line, and that's this part. Okay, so maybe I add some more comments here. So this was the opt vocabulary at the top. Here we have to, or we initialize the full system, which is the core of our VSLAM. VSLAM being visual simultaneous. Oh my god, it's really late. Simultaneous. I think it's like this. Sorry if this is wrong. Visual simultaneous localization and mapping. Okay. The part below here is initialize the graphical user interface GUI using the pangolin library. Okay. Good. a lot of stuff to do, but now we are at the point where we can actually start the main loop. And the main loop is located on a thread. This is the main loop, which runs on a separate thread. So what we will do is the following. Let me turn down the volume of the music. It's really, really loud. Okay. Maybe let's switch the music here. Okay. So what we will do here is we define a thread. This will be a whole block which tells us what is happening in this main loop, and then we will join this thread to our currently running main thread, and once this is joined, this thread is being executed, which of course will take a long time because there are many images usually we want to process, and there is not easy computations to be made, and therefore this will take a time, but it's on a separate thread, so our program will not hang. Okay, so let's create this thread, standard thread, run thread. You can call it as we wish, but here we need to put in a function with a function body, and I think we can then put a semicolon. Yes, this should be that. And here inside this body will be the main part of, the main operation of this Visual Slam, the main logic. But after that, we'll check if we have a viewer. And if we have the viewer, then we want to run the viewer. Viewer run. And we add the comment from the original code base, which is macOS should keep this in main thread. So it's this operating system specific operation, but we are on Linux Ubuntu at the moment, so we will not bother with the Mac and Windows at the moment. After the viewer is running, we say we have this run thread from above, run thread dot join, and then we have the viewer. So as far as I know, this will hang, or this will take a while. And then after the run thread is finished, then we say viewer, we want to save your result as a PLY file, which we define here, which is called the point cloud PLY. And then we log an info, which is called exit now. And then we return 0. And this is it. So things that are missing at the moment is the viewer. Therefore we add a to do here. And of course, we also need to do that here. But this thread, I think we can add the thread here, which should be an include in the beginning of this code file. Let's check. We have this IO stream, which is used for the cout commands. Then we can include the thread from the standard template library. And I think this should fix this error here. And by adding this, we should be able to test our code so far. So let's save it. And let's see if it compiles. Make project. There are a few warnings because we are not using variables. That's fine. But it was compiled and linked. And now we can run this code. And we'll see what is given here. Okay, so it is loading a gamma calib file from this argument. And then warning, logging before init Google logging is written to standard error. Interesting. So there seems to be some instruction in the later includes. Let me just rearrange that, sorry. So there's a warning here that we need to initialize the Google logging. And this seems to be done in some other file. Let me quickly check if this is really the case. So when I open this in a terminal, let me quickly make a backup folder to store the results from the last run. I want to run the LDSO sequence once again. And let's stop that. Okay, but now I can see that here the warning is the same, so this is something we need to fix on our own. But I want to concentrate on finishing the LDSO Twitch version, so I will not fix that. Okay. Next we need some other libraries we need to include here. For example, we need the clocale library. We also need the csignal. We need the cstandardlib. And we also need the cstandard input output. I think we do not need that. So that's a to-do. I think that can be removed because this should contain the printf commands. Then we need another include for the uni standard.h file. And we also need the system time.h, which will be useful in a minute. And then later, at some point, we will also include a local file, which is the front end for the system.h. And also the dataset reader.h. And this should be all of the includes we need there. We also need this namespace for the LDSO, which is not used at the moment. And of course we need to add all the settings and so on and so forth. Okay, we will finish this part by completing this run thread here. So let's go through it. We have this main body here, which will now be filled with the individual images, the frame IDs, the frame IDs we want to process. So we need to introduce a standard vector which contains integers, and these are the IDs to play. And we also have another standard vector consisting of doubles, which contains the times to play at. Then we have our for loop, which will first iterate all of the images that we have and fill up those arrays. So the arrays for the IDs and the array for the times. So we make a for loop here, which starts with the integer I, which is set to L start. Then we check if I is greater or equal to 0, and if I is less than, not count, but reader, and then here the get num images. So the total number of images. And we also want to check if the L increment times I is less than the L increment, I think. L increment times L end. And for the iterations, we want to increment I by L increment. Okay, in this code here, we now want to fill up the arrays, which means that we first want to use the IDs to play and push back the current ID or the current index. Next, we also want to use this times to play at vector and check if times to play at size is equal to 0. And if this is the case, then we want times to play at pushback a 0 casted to a double. Else, we want to define two variables, a double ts this, and we take this information from the reader. There will be a method that tells us the timestamp, get timestamp of IDs to play at the position IDs to play dot size minus -1, and we also have a double ts previous or pref equals reader get timestamp and here we have again the IDs to play dot size -2. So we get from the size to the current ID and to the previous ID by using those two statements. And once we have that, we say we have the times to play at dot pushback. Now want to pushback times to play at back plus on the absolute value of the floating point number fubs ts this ts pref, so difference between those two timestamps divided by the playback speed. Okay, fabs is undefined. Which is weird. Fabs. Okay, it's probably defined in some other include file. But this is not a problem at the moment because this is something we cannot use anyway because we do not have the reader at the moment. So I will add this as a to-do for now. Okay, so this is about the timestamps. Let us comment that. Prepare the correct timestamps for each image. So the timestamps are necessary if we want to do something with speed. So if we want to, I don't know, integrate an acceleration or a turn rate, for example, we usually want to have the information, how long it took between two images for them to be taken, so we can use the proper integration about or using this time information. So this will come into play at some point. We need to prepare that, and this is what we have done here. And next we have another vector, which this time does in fact contain the images and their exposure. And this is a pointer to the preloaded images. And if preload is set to true, then we want to print something to the screen. So cout loading all images end line. Oh, sorry, you cannot see it. I'm very sorry. Okay, this is the image and the exposure. And we need to load those images or preload them by using a for loop with the integer I equals 0, and then I is less than integer IDs to play dot size, and then II plus plus. What do we want to do here? So we iterate through all the IDs we want to play, and from the IDs we can get the image index, which is then called int I equals IDs to play, II semicolon, and then we use preloaded images, so our array from above, dot push back the image from the reader. Get image I. And this is it. So we just get all the individual images, and by executing this command, the image will, as far as I think, get loaded onto the disk, and then we have all the preloaded images stored in this array, and then we can process them in our main loop. Okay, once again we need to unfortunately comment that out, but not without, or not before we provide an explanation. Load all the images we need in a data structure in our memory. Probably not the best description, but I think that is what is happening here. Okay, after that, we want to define a struct of data type timeVal, time value start. Then we want to get the time of day and put it into the time value start. And this is the restrict time zone. Time zone must be a struct time zone. Okay, we will not pass a time zone. That's fine. We are only interested in the relative time. that the algorithm is taking. So what is happening here is we want to start a stopwatch, let's say, in order to measure performance on a data set. And we have a clock type started equals clock, and we have a double of s initializer offset equals 0. Okay, now that we have started the time, we will obviously do something that will take some time. And this is where the main loop comes in. Here is the main loop of the vSlam implementation. We will skip that for now, because this will have some lines of code as well. And just finish what we have here, because in the end, we want to say full system. And for the full system, we want to block until mapping is finished. So the full system will be mapping the scene, and until this is taking time, we just want to stop here until this is finished. And if this is finished, we want to once again define another clock type and call it ended. And we want to measure the clock. And we want to have a struct of time val end, and get time of day. We pass the reference to the time val end, and again no time zone. Then we want to call full system, print result, and we want to print the result to our output file. Where the second parameter seems to be an information about loop closure, if we want to activate or deactivate the loop closure for the results. So here, once again, we call another the same function, print result, output file, but here we add an extension called no loop, where we deactivate the loop closure. And this is useful later, useful for data analysis, statistics, then we define an integer for num frames processed is equal to the absolute value of IDs to play at position 0 minus IDs to play of the last value back. So this difference will give us the total number of frames that are processed, because the IDs can be, they can vary, there can be skipped frames in between, the offset can be different, and therefore we need to compute that here. And then we calculate a double for the number of seconds processed. We quickly turn down the volume of the music. Double num seconds processed equals f_ups reader. And we use the reader to get the timestamp at the position IDs to play. The first ID we want to extract here. And then minus the reader. The reader. And from the reader we get the timestamp at the IDs to play dot back, which is the last entry, the last element of the vector. And by computing this difference and taking the absolute value of that, we get the number of seconds processed. Then we get another double, which is called milliseconds, taken single is 1000 times ended minus started divided by, cast it as a float, the clocks per second. So the started and ended are clock types, and we divide it by the number of clocks per second to get the difference in seconds, and multiply it by 1000 to convert from seconds to milliseconds, and therefore we get the milliseconds taken for a single image. No, not for a single image, but for the single processor probably. So this is the whole time that has passed between starting the stopwatch and ending the stopwatch. I will probably add this comment here. Okay, then we have the statistics, and we also need another double. Milliseconds taken MT, which is probably standing for multi-threading, I believe. That means that the single is probably a single thread, and MT is multi-threading, which is computed with as initializer offset plus the time value end dot time value second minus time value start dot time value second, and this multiplied by 1000, which converts to milliseconds, plus we not only take into account the seconds but also the microseconds, which can be done by time value end dot time value usec, or subseconds, it's also called subseconds here, minus TV start, time value start, dot time value microseconds. And then we divide by 1000. Not sure if this is microseconds now. Probably it's not. Oh well, if we want, yeah, it's microseconds indeed. If we divide microseconds by 1000, we get to the milliseconds, and this way the end result will be in milliseconds. And that's fine. So we can finish this off here. And now, of course, we want to display the statistics, which we will do with the cout. And then we'll print something, and then we will add the end line. Now we need to make a new line here, like this. Let's prepare this here. Okay. So in the beginning, we want to make a new line. Then we want to print this double line. And then we want to print the statistics, which means we have some frames with, oh, this is getting complicated, FPS. I'm trying to convert the statements from the printf to the cout, so I need to think a little bit. Sorry about that. So we have the number of frames, which is, of course, the num frames processed. And then frames. But then here we have the num frames processed divided by num seconds processed to get the frames per second, FPS. Then in this next line we have the milliseconds per frame, single core, and later we will have the milliseconds per frame, multi-core, and then we have a factor for a single core, and then we have a factor for the multi-core. And now what are those factors here? The milliseconds per frame for the single core are milliseconds taken single divided by a number of frames processed. Then this was for the single core, and of course we also have a similar thing for the multi-core, multi-threading, but this needs to be casted as a float number of frames processed. Then we have the a value of milliseconds taken single, a 1,000th of the milliseconds taken single divided by the number of frames processed. And similarly, we have this taken for the multi-threading. Yeah, with concatenation of the string here. Let's remove those spaces, then it should be fine. We can also add another double line here. Oh yeah, this is missing. Okay, but this should be fine. And lastly, on this thread, before we focus our attention on the main loop, lastly, we want to check if the setting was set for log stuff. And if this is true, then we want to open a file, an output file stream for TM log. Or called TM log. Then we open this log. TM log open logs time.text standard IO stream trunk or standard IOS out. Then TM log 1000.0f times ended minus started divided by float of clocks per sec times reader, and we get the number of images again. Next, we want to add a space. And in the next line, we add the time value end dot time value sec minus time value start dot time value sec times 1000, and we add that microsecond difference as well as we did above. Time value end, time value usec minus time value start dot time value usec divided by 1000, and this whole thing will be divided by a cast to float of the reader, get num images, and end line. Then we take the TM log dot flush and tmlog dot close. And this is the end of the thread. We are still missing this main loop here, but after implementing that, we will be finished with at least the instructions that we need, which we then need to fill out over the course of the next parts. So I will add this as a to-do here, because we are not having the settings at the moment. I think I will also need to put the to-do around this part. Unfortunately, I'm not sure why this f-apps is missing here. What is the correct include that I need for the f-apps? Not sure at the moment. I'll quickly look it up. C++. C math. Interesting. Let's try that. C math. Because if this works, we will actually have... Oh no, the reader is missing. Ah, that sucks. Unfortunately, cannot get the reader, but we will do it like this. I will just write a random number and add a to-do here, so that we will have at least why is this not working? Ah, I'm missing a semicolon, of course, once again, as usual. Okay, now we need to comment out this as well, to do. Oh, that's much nicer with 3 slashes. Okay, we need to comment out this as well. There's an error here, but that's fine. We'll come to that. I think the rest is working. I'm not sure if this is a problem that we will not have any IDs to play. The IDs to play will be, this will be empty. And this might throw an error if we try to access the array if it's empty. Not sure if this is a problem, but I think this will lead to a problem. But we'll fix that. Okay, let's finish up the last part of this main loop, or just finish this main loop. Okay, so here we want to loop through all the IDs to play. And these are the images that have been loaded in the data loader. Okay, so we have a for loop, which is of course an integer that we start with, I equals 0, then I is less than cast to integer of IDs to play dot size, and then we have I incremented. Okay. The first thing we do is to sleep, while we have the setting pause equal to true. While this is true, we call uSleep 5000, just microseconds, I think. Microseconds. Okay, 5000 microseconds. Okay, so 5 milliseconds. If I'm not mistaken, we get to sleep. And we check if not, full system initialized. If not full system initialized, then we get the time of day. We get a reference to the time value start. And once again, we do not pass a time zone. Then we define started as current clock measure. And set the S initializer offset to times to play at II. Okay. Next we have the integer I, and we set it to IDs to play for double I. So we use the current ID to play. We get the ID and store it into the variable I. And now we know, for example, if we are at image with the number 32 or something, we want to use this index to get the correct image. And we store the image in a data type called image and exposure. And this will be a pointer for image. So this is the main data type for an image. If now preload is set to true, then we want to set this image by looking up the array of preloaded images. Preloaded images. Why is it not showing up? At index II. Let me quickly check why this is not working. Preloaded images. Okay, because it's defined here and this is commented out, so it's not finding that. Okay. Yeah, that's the problem with something that is missing. We cannot use it. If preload is not true, so else, we want to set the image by asking the reader to get the image. And this time we use the index I and not II. because these indices are different. II is from the current for loop, and I is from all the images that have been determined in the beginning, taking this index from there. So the reader basically has a different index structure than the preloaded images data structure, which is a bit confusing, but this is how the LDSO is constructed. Next, we want to see if we need to skip a frame. Bool skip frame is false. But if the playback speed is not equal to 0, then we might want to play back the image sequence faster. So this is why we need to calculate if we want to skip the frame. And we do this by introducing a struct, which is called timeVal now. Then we get the time of day. We pass the time value now with a time zone of null. Then we calculate the s since start is equal to s initializer offset plus, then we have again our time value now dot time value sec minus time value start dot time value sec plus time value now dot time value usec minus time value start dot time value usec and this will be divided by okay, now we have seconds. Okay, and it's fine. Divided by 1000 times 1000 to get from microseconds, I think. Microseconds to milliseconds and then to seconds. Let's rearrange that. No, it's ugly. Let's keep it like that. If s since start, now we want to check how many seconds have passed by using the times to play at array at index ii. Okay. Now this line is commented out in the LDSO, but usually what is written here is uSleep int and then times to play at ii minus s since start times 1000 times 1000. I will decide later if I can remove it. As it's a comment anyway. But the else if is important. condition is s since start. Oops. Start. Is greater than times to play it at index II plus 0.5 plus 0.1 times II modulo 2. Okay, whatever this is. This is weird. Plus 0.5 plus 0.1. Okay, what do we do here? We want to see out something. That is skip frame. And then we add the II. Play at play at times to play at II. Times to play at. Now it is something else, namely s since start. S since start and exclamation mark and end line. End line. And next we want to set the skip frame to true. So with this magic condition here, where I'm not sure what this means, to be honest, we can set the skip frame to true. So probably this is some way of defining a margin. Maybe to account for floating point errors, but it's still not clear to me, to be honest, what this means. Okay, next, if the playback speed is not equal to 0, then we skip a frame. Maybe we skip a frame. Now we check if we do not skip a frame. If we do not skip a frame, then we simply call full system add active frame, the current image and the index I. After that, we delete the image. So if we have skip a frame, then this function is not getting called, and we iterate to the next loop iteration. What I want to add here is a comment that here the magic is happening, which means that this method add active frame from the full system will get the current image that we have loaded and we are currently processing in our main loop, and from this image the system, the Visual SLAM system, is either initializing or processing the image information as usual. So this will be a very important method we will take a look at to really understand what is happening behind the scenes if we get an image and we process the individual pixels of the image to get a twofold information from that, namely, first one being the current relative pose for generating the whole trajectory and getting the current point cloud. So this will be very interesting to see how this is working. Okay, so after this active frame has been added, we are finished with the full system, and we need to I wanted to say to take out the trash, but there's a different word for that. To clean up, yeah. So this is the cleaning up. Which means that we need to check if the full system does tell us that the initialization has failed. And if the setting full reset requested is active. This is, for example, something we can set in the user interface. There's a button called reset, and pushing this button will toggle this as true, and then something will happen. What will happen? We'll check if the II is less than 250. Once again, what was II? This is for our main loop, the current ID that we want to play. If this is less than 250, which is weird, but I think it's a hack, I would say, or the setting full reset requested is true, then we want to log an info to the console, namely init failed resetting exclamation mark, of course. Then full system is then overwritten with a new shared pointer of type full system, with a new full system with the vocabulary file. Then when we have this new full system, of course we need to set the initial information about the photometric calibration. So we need to set the gamma function from the reader and get photometric gamma from that. And also full system linearize operation is equal to playback speed equals 0. And then we need to check if we have a viewer, because if we have a viewer, we need to associate the viewer to the full system. So we need to first take the viewer and reset it. Then we sleep 1 second. Oh, 1 second is long. And then we say full system. And for the full system, we want to set the viewer as our viewer. And lastly, we have a setting of full reset required, which is equal to false. And as a last step, we want to determine if our full system is what is called is lost. If this is the case, then we want to, sorry, I always forget that the lower part is has an overlay. Log info lost. No, lost. And we then break the loop. And we're finished here. Okay, so what does it mean if a full system is lost? This can happen, for example, if the camera is moving very, very quickly, or if we have an environment that does not provide sufficient information for the LDSO to initialize, or maybe also has misleading information. So basically the environment is changing very drastically, which can happen by a quick camera movement or a quick change of the environment, for example. Then the system is lost and the LDSO does not know what to do next and is basically just standing there and lost. Okay. So now we have some errors here. We need to see what we can keep and what we need to comment out. So this setting pause is not available. That's why we'll comment this out. Then the full system is not available. So we also need to comment that out. We do not have the image and exposure yet. So we comment out that as a to-do. Now what about the other timing stuff here? It should work. Okay, now we have, of course, this very important part, which is not implemented yet. So it's in to-do. Okay, IMG is not defined because we do not have the image and exposure yet. Now here, the whole resetting of the full system is not yet available. So we need to comment that out as well. Here the full system again is not yet available. So this is also commented out for now. But other than that, there should be no errors. And we can try to compile that code, which should work in my view. But running the code will, I think, lead to problems. But let's check it. So make project. Okay, compilation and linking was successful. And now we see if we run that. What is happening here? Core dumped. Yeah. And this is a segmentation fault, as we can see here, which is very unsatisfying. But as I was already suspecting, this has to do with the array. Let's check it here. So this should be not a problem. This should also work, this as well. Now with the thread. Here we have the IDs to play and the times to play at. We are not filling up those arrays. And until we do that, and until we are not using the arrays, which is the case already with size, we should be fine. So maybe this is a problem, but definitely this is a problem if this is starting to get into the loop, because there is no index available in the IDs to play. So this is definitely a problem here. And this will continue here as well. So everywhere where we have an access to a memory, to our memory on the system, and if this memory is not available, we will have a segmentation fault. So I'm afraid I will have to, same here by the way, I'm afraid that I will have to comment out almost everything, and we will not even have an output for the milliseconds that have been processed. But to be honest, I did not expect anything different, because what should be happening here if we do not have the main functionality implemented? So I think this will be a necessary step to comment out a lot here. But let me quickly think. There shouldn't be a problem if this is not even entering here, because I would say the size will be 0, and therefore this will be evaluated as being 0 less than 0, which is false, and therefore it will not step into this for loop here. So I would say that we can leave this part here uncommented, but the problem will rather be by accessing this specific index 0, which is not available. So I would say I will comment out this and try to recompile. Segmentation fault. Okay, let's see. This should be fine now. Okay, it still compiles. Okay. At least we have this part exit now, which is line 603. 603. We have this login for exit now, so we have executed the run thread. We have joined it to our other threads. The run thread is where basically the magic is happening, but not only the magic, but also in this main thread. Let me check. In this run thread, we also have some different parts, which is more of a management, like defining the IDs of the images, the timestamps, preloading images, starting the stopwatch. But the really interesting part is happening here in this for loop, which will iterate through all the images, which are stored in these IDs to play. And for each image, of course, also it's calculating if it should skip a frame. This is also management, But if it's not skipping a frame, then here really the real, let's say here I would say the real nice magic is happening to stress that. So really what it boils down to is this full system and add active frame. Here the main logic of Visual SLAM technology is happening regarding the direct SLAM that's implemented here as the LDSO, and all the other stuff, which is a lot of code, is only used for management and for housekeeping. But still, I think it's amazing to see how many steps need to be done to get something even running as simple as a Visual SLAM system. And of course also logging stuff, saving files, the point cloud, and also this output file for the trajectory. This needs to be printed and visualized as well. So there's also a viewer needed that is visualizing the trajectory and the point cloud, and you should be able to move around to see the images. This is a whole lot of overhead, which is really necessary to see something on the screen. Of course, you can have a terminal output that looks like this, but then of course you do not know what is happening in the background, if something is working or not. And for debugging, you really need a nice visualization. So this is also something we need to create. As you see, it's a lot of stuff we need to do here. But what we have accomplished today together is to see, okay, what is the framework, the algorithmic framework, and what are the components that are needed to prepare the data that we have for the final processing in the core of the full system. What we will do in the next parts is we will start from the beginning of this main function here and try to get rid of all the to-dos here. So we need to find a way to get the settings. The settings will be in a different file. This file needs to be included, maybe not in this main file, but in another file. So we will maybe prepare the files first and leave them blank and try to get the settings to work. And with the settings working, we can then fill up the main functionality of the Visual SLAM. That's the plan. Of course, if you have ideas or if you have suggestions how to go about that differently, feel free to tell me that. But for now, I would say this part is finished. We are unfortunately not seeing anything on the screen yet, but we will get to that, hopefully. It will take some time, but if you bear with me, then we will get that accomplished together. Thank you very much for listening, for sticking around and being interested in the topic. And now I wish you a great, for me it's about 4 AM, so I will go to bed now and see you next time. Goodbye. Thanks for watching.